In this video, we are going to talk about rational functions. Rational functions are made up of two polynomials that are being divided, and because they're being divided, we create points of discontinuity, and that is a whole or an asymptote. That point of discontinuity affects the domain, you can find the wholes by simplifying the expression and seeing what divides out to 1. You can get vertical asymptotes by setting the denominator equal to 0, and then we also have a horizontal asymptote, which you find by dividing the polynomials. There are also some shortcuts for that, and those go along with what happens when you divide the polynomials. So I'll show you that when we do an example. The definition of a horizontal asymptote, which we'll use later, is a line that the function approaches as x goes to infinity and negative infinity. That definition should look familiar. It is end behavior, which we've talked about before. And you use that when you were evaluating polynomials. Here are 7 steps for graphing. These are very useful, and if you follow those, then you'll be able to analyze and graph any function. All right, I'm going to leave example 1 and 3 for you, so we're just going to do example 2. So in this first example, we have x squared plus x minus 6 over x squared plus 2x minus 8. And before we factor that, we're going to find the y-intercept and the horizontal asymptote, because you can find those really easily in this original unfactored form. So to get the y-intercept, we're going to set x equal to 0. When you do that, you get negative 6 over negative 8. That reduces to 3/4. So your y-intercept is 0, 3/4. To get the horizontal asymptote, you divide your polynomials. So I'm going to take x squared plus 2x minus 8 going into x squared plus x minus 6. X squared goes into x squared once. So then what you're left with is negative x plus 2. The negative x plus 2 is just the remainder. I don't care about that part. I just need how many times x squared goes into x squared, which is 1. So your horizontal asymptote is y equals 1. The reason I don't care about the remainder is because of that definition of a horizontal asymptote, that I'm concerned with what happens to the function as it heads out to infinity. And so this negative x plus 2 has no bearing on what's happening all the way out at infinity, only that initial part of dividing the x squared into the x squared. When you divide the long way, it goes along with these shortcuts up here. We actually use the second shortcut, that if the degree of the numerator and the denominator are the same, which in this case they were both x squared, you can find the horizontal asymptote by dividing the leading coefficients. The leading coefficients in our example were both 1. And so when I take 1x squared dividing into 1x squared, you just get 1. So again, the best way to do this is to divide by long division. You're going to use that when you find a slant asymptote. And those shortcuts that are laid out at the beginning of the notes, those go along with what happens when you divide the long way. To find a slant asymptote, you have to divide the long way anyways. There is no shortcut for it. Alright, so now to find the rest of the things that we need, we're going to factor this function. So that factors into x plus 3 times x minus 2 over x plus 4 times x minus 2. You'll see that we have x minus 2 in common, so that's going to create a whole at x equals 2. The reason there's a whole there is because if I plug in 2 for the x values on those, I get 2 minus 2 over 2 minus 2, which is 0 over 0. And that 0 on the bottom creates an undefined point in the graph. And so it's a whole there. Usually when something's undefined in the denominator, we say it's an asymptote, but because the numerator and the denominator both have that common factor, that x minus 2, they divide out to 1. It actually creates a whole and not an asymptote. All right, so to find where that whole is, we know the x value is 2, but we need to find the y value. To get the y value, we're going to plug the 2 back into what is left of our equation. So we plug it into the x plus 3 over x plus 4. So I'm going to take 2 plus 3 over 2 plus 4, which is 5/6. So our whole is at 2 comma 5/6. All right, now we can find the x-intercept and the vertical asymptote. The x-intercept is when y equals 0. So I'll set that equal to 0. So 0 equals, and I can just use what's left over. Remember that whole divided out to 1, so I'm not using it anymore. So I just have 0 equals x plus 3 over x plus 4. To get rid of the denominator, I multiply it over, so it goes away, and I'm just left with x plus 3. So an easy way to find the x-intercept on these rational functions is to just set the numerator equal to 0. So if that equals 0, then my x-intercept is at negative 3 comma 0. To get your vertical asymptote, you set the denominator equal to 0. So x plus 4 equal to 0 means we have a vertical asymptote at x equals negative 4. Lastly, for our domain is going to be all real numbers except for where it's undefined, which is happening at the vertical asymptote and at that whole. So my domain for this function is negative infinity to negative 4, negative 4 to 2, and 2 to infinity. And now I can use all that information to make my graph. So I have a horizontal asymptote at y equals 1 and a vertical at x equals negative 4. When you draw these on your graph, make sure you label them. Labeling is always good. Alright, now I can plot my x and y intercept. So 0, 3/4 and negative 3, 0. And then we had a whole at 2, 5/6. So I got a hole here. And I can connect these to make my graph. But then the next question is the other side of the graph in this upper corner or the lower corner? The easiest way to figure that out without plotting points is to look at the multiplicity of the factors in the denominator. So if we look back at the beginning of our notes here, when you look at the multiplicity of the factors in the denominator, if it's even, then either side of the asymptote, your graph is going to travel in the same direction. And if it's an odd multiplicity, they're going to travel in different directions. So think about when you did polynomials, and if you had an intercept that had an even multiplicity, it bounced off of that point and went back in the same direction it came from. If it was an odd multiplicity, it just went straight through and kept traveling in that other direction. So with this example here, if we look at our asymptote factor, x plus 4, that has a multiplicity of just 1. So it's an odd multiplicity, which means I need to be traveling in the opposite direction as my function. So if this side of the function of the asymptote is going down, then on the other side, it needs to be going up. And so we know it looks like that. You can label this as whole so that we know that's a whole and not a closed-in circle. One last thing. When you check this in Desmos, if you graph the x squared plus x minus 6 over x squared plus 2x minus 8, you will see, well, it's hard to see on the graph, but if you travel along the function, you'll find that there's a hole at 2 where it's undefined. But then if you graph just the x plus 3 over the x plus 4, what's left when I take out the hole? It's going to look exactly like the original f of x function. The only difference is there's not going to be a hole at 2. So when I have this original function x squared plus x minus 6 over x squared plus 2x minus 8, it behaves the exact same as x plus 3 over x plus 4. It just has a hole at 2. And if you have any questions, let me know. That's everything.